Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss the concept of orifice meter. In our previous lecture, already we have discussed regarding the venturi meter, and there I have told that why this orifice meter, venturi meters are used, because these are the practical application of Bernoulli's equation, and these are the meters are used to measure the rate of flow. So you can say this is the device which is used for measuring the rate of flow of a fluid when it is flowing through a pipe. Okay, and this device also, if you compare with the venturi meter, it has some advantages and some disadvantages also there. So in the advantages, if I say, so this device like orifice meter, it is cheaper in price. So this cost of this orifice meter is less. Okay, or you can say cost of the product is less. This is first one. And apart from that, I can say this is easy to install in a pipe. So installation is easy. So this is the second point. Installation is easy. And the third point, I can say, this, like, though you can say it is a simple in design, the design of this orifice meter is simple, and so that we can say it is easy to use. Okay, simple design also I can one. This is one advantages, and uses also easy. So these are the some advantages of this orifice meter than the venturi meter. But the main point when it is coming to the disadvantages is actually it won't give you the accurate value of the flow rate. So the accuracy is a matters of this device compared to the, if you compare with the venturi meter, so accuracy is less. Okay, and similarly that means exact rate of flow you won't get in that. So that is one of the matters in the orifice meter. Anyway, let's discuss about in details of this orifice meter. So as I told you, this orifice meter is working, as per the Bernoulli's equation principle, and these are the, we can say, practical application of Bernoulli's equation, and where we can measure the rate of flow. We can measure the rate of flow. Now, how it is, installed in this? This manometer can be used like, this kind of manometer, YouTube type manometer, we can say in this. So it varies, no issue. We can use like this. Okay. Anyway, so suppose there is a pipe is there, and the liquid is flowing through a pipe. Okay, and in this pipe, any point of this pipe we can measure, we can put one orifice plate or orifice meter in that. So how this plate is there, and in this pipe, suppose, so like how we can put the orifice meter or orifice plate in this pipe. So these are the two different, flanges are there. Flanges means which will be used to hold some kind of other equipments in that, and these flanges will be tight, by nut and bolt. We can tight this one, and in this flange we can put this orifice meter in between this. Okay, and before that we have a pressure gauge used to there, which will be give you the pressure value of this, water. Okay, what is the pressure at this point? What is the value of this pressure? We can measure that one. So that will be give you inside the pipe what is the pressure value is there. We can get it here. And after crossing through this orifice plate or orifice meter in this, at this point which is present, again one more pressure gauge will be there. That will be give you the again the pressure value of that. This is I'm talking about when it is used in the industry areas. Okay. Now similarly, if you want to look after this orifice meter, so let me say you another one thing. This orifice plate is nothing but, it will be a circular plate type will be there. Okay, the circular plate type will be there, and not this much should be there. This is little bit, yeah, it will be like this. So this plate is fixed inside in between this one. So, and it will have a like a serpent edge type will be edge. This edge will be the little bit serpent type will be there, sharp type here. If you see this plate, now see this is like, sharp type is there here at this point. So when the liquid will be flows in this, now it's going to be reduced this, reduced area of the flow. Like this, it will be flows through that. Okay, so you can see here. Now, due to this, there will be a change in velocity, as well as we can say some kind of pressure also will be difference after this. Like before this, what is the pressure value will be there, and after that, what is the pressure will be there. So due to this pressure difference in the water, because it was slightly compressed here, and after crossing this orifice meter, we can get some pressure difference. So due to the pressure difference in this, so we can get a difference in the manometer. There is a liquid difference within the manometer. So what is the difference in this manometer? That also can be measured, because in the manometer we know that here we used to keep some liquid which is mostly mercury used to used here, and due to this pressure difference there will be a changes in this level of this mercury. Okay, so that also we can identify from here. Okay, so this is about the orifice meter and its plate. Okay, and the diameter of this orifice meter actually this used to vary. The diameter of the orifice plate used to vary from 0.8 to 0.4 to 0.8 times than the pipe diameter. Suppose this is the pipe diameter is there 20 centimeters, suppose, then this will be like 20 into 0.4, so it will be 8 centimeter. So similarly, sometimes you used to take as a 0.5 times diameter of the main pipe. So this is the main pipe is there. What is the diameter of this? This will be half of that. Okay. So here the orifice meter is installed at the pipe. As I told you, this is very simple in design. Now we'll find out. We will derive this equation for the orifice meter. So to derive this equation for the orifice meter, here I have taken a section 1 and here it is section 2. Okay, these two different sections we have taken in the pipe, and you can see at this point also we required some kind of value. Value means the characteristics of fluid. So like what is the pressure at this point? So I can say P1 is the pressure at the section 1. Similarly, the velocity of the at the section 1, that is V1 I can write, and similarly I can write D1 is the diameter of this particular section 1. So D1 is there means we can identify what is the A1 at this particular section. So this is all about the section 1. Similarly, if you come to section 2 at this point, after crossing this orifice meter at this point, now at the section 2 you can see similarly it is P2, V2 and D2, and similarly A2 also you can find out from here directly. Okay, so these are the some parameters are there for the liquid. And now if I apply the Bernoulli's equation for this section 1 and section 2 when the liquid is flowing the pipe, so we can write as you know that Bernoulli's equation, that is P by rho G plus V1 square by 2G plus Z1 equal to P2 by rho G, and this is V2 square by 2G again and plus Z2. So this is the main equation, like Bernoulli's equation. And now you can see Z1 and Z2, this is the datum height of the fluid. Datum height means what is the level of this fluid which is flowing in the pipe from the reference line. If you take this is the suppose reference line, so what is the distance of this fluid at the section 1 and what is the distance from this reference point to this section 2. As this fluid is flowing in a line, in a pipe, so if you take the center line of this pipe, then the distance of this center point of this line flows and this one both are same. So this Z1 height and Z2 height, okay, both are same, so we can cancel this one. Then what I'll do, I can take this P1 and P2 one side and V1 V2 one side. So what I can write for this one, I can write P1 by rho G, okay, and this is minus P2 by rho G equal to, this is V2 square by 2G minus V1 square by 2g. Okay, and remaining z1 z2, as I told you, both are same, so we can cancel that. Okay, now this also, as I told you, this also you can write, this is the difference of the differential head. Okay, this is the differential head. So here also, if you can if you want to add this z1 and z2 in this particular term, also you can add it, or you can keep it this one as it like. So this term we can write differential head like h equal to, now here I can write like v2 square minus v1 square divided by 2g, and now here I can write again this v2 square minus v1 square, and this 2g I can keep it here, so that is 2gs. And again what I'll write, suppose I want to identify some velocity of any point, so I can write directly v2 equal to what, and this 2g into h, I can write 2g h, and this minus v1 square, let take it to in the left hand side, so that is going to be plus v1 square. And as I told, and as I written here, v2 square is gone, so the square will become this side, and again we can write this is root over of this. So this one again we can give equation 2. Okay, so this is first step of this part. Now here again at this section, if you see at the section, okay, we have a vena contracta. The vena contracta means the area of this flow is minimum at this point. Okay, the area of the flow will be minimum at this point. Okay, that is vena contracta. So at this point we can see the A2, because here we have taken A1, so section 2 we have the area A2. So to find out, okay, what is the concentration of the orifice? Okay, what is the concentration of the orifice, in the sense what is the how much water is going to be reduced at this, what is the velocity is going to be reduced, and how much changes happened at this point at this orifice plate, and from this orifice plate, because you can see the water is converging here. Okay, the water is converging here, and after slowly it is going to be diverged. Okay, so up to a limit here. So here we can get this. So now what I can write, so if you consider this is the orifice plate at this point, so we can write A naught here. I'll write here at this point, A naught is the area of the orifice plate. Okay, area of the orifice plate. And now what I can write, let me write one term, this is cc equal to, I can write area A2, like up to this area, as I told you, from this orifice meter to up to this second section, so that is A2 divided by A naught. So this cc is nothing but that is coefficient of contraction. Okay, so how much contraction in this point from here to here? So to find out this one, I have written the cc. So cc equal to, we can write this value, and here I can write also A2 equal to A naught into cc. Okay, this is one value is there, and this one we can write some equation also. If you want to give equation, give equation 3. Now the value of A2 is there. This A2 reminds me the equation of continuity equation. So we know that from the continuity equation we can write, because it is a flowing through a pipe, so we can write as continuity equation, we can write A1 V1 equal to A2 V2. Why I am writing this one? Because in this equation, if you see, V2 term is there, V1 term is there. So I want to just solve it in one term. Okay, any one term I want to keep it, so that it will be easy for us to identify. Now here I can write the value of V1 equal to A2 into V2 divided by A1. Okay, now if you see, A2 by A1 into V2, so this is another equation, equation 4. Now put this value of V1, okay, in the equation 2, in this equation. Which equation? This one. So if we put the value there, then what we'll get here, because V2 equal to, we have seen root over of this one, so let's write the same thing here, that is nothing but 2gh plus v1 square. V1 square is nothing but we got here v1 equal to a2 v2 by a1. So we can write, yeah, one more thing, a2 place we can put the value of a naught cc in this place. Okay, so here also we can write one more term, that is a naught cc into v2 by a1. So here we can write v1 square, that is nothing but a naught square, and this is v2 square, and this is cc square divided by a1 square. Okay, so this is v2, in point of v2 we can write this one. Now again, what we need to do, we need to solve this equation, and we need to find out a simple term from the equation in terms of v2. So what we'll do is this, let's solve this one and let's write. Okay, I'll go to the next page so it will be easy for us. Yeah, here we can write. So what we have written, v2. Okay, now what I'll write here, I'll make it square this side so that root over will be removed. So I can write here v2 square equal to, I can write whatever is there in that side, and that is 2gh plus a naught by a1, I hope, a naught by a1, that is square, a naught by a1 square into, which is c square into v2 square. Now this C, we have changed the v1 into v2 term, so both side v2 term is there. Now what I'll do, I'll take the common of v2. As for taking the common of v2, what I need to do, I need to take this term to the left hand side. So directly in the same line, let me write here. So I'll keep 2gh one side and v2 square one side. So let me write v2 square minus, what we'll get here, a naught divided by a1 whole square and cc square into v2 square equal to, this is 2gh. Okay, now here I'll take the common of v2. So here I'll take the common of v2. So what will get, v2 square square bracket start, so 1 minus, this is a naught by a1 whole square, and this is cc square as usual, bracket close, equal to, I can write 2gh. Okay, now again what I'll do, I'll convert into v2 term. So directly I'll write v2, I'm not writing v2 square, I'm writing only v2. So what will happen, this 2gh divided by, this one term is there, 1 minus, this is a naught by a1 whole square into cc square. And now we can see initially it was v2 square, so I can write v2 square. But now what I want to do, I want to remove this square and I want to keep this square in this side as a root over term. So I'll keep both the root over in this side. So I can write v2 equal to root over 2gs by 1 minus a naught by a1 square cc square. Okay, so this is the term. Now again, what is your final aim? Our final aim is to, we need to find out the discharge. So discharge equal to, we know that q equal to a1 v1 equal to a2 v2. Any of the term we can consider here. Either you can consider a1 v1 or you can consider a2 v2. Any of the term you can consider. So what I'll do, I'll write, this is q equal to, let me consider a2 v2. So here in the v2 term, I can put this value. So what will you get finally here? a2 v2. Okay, so a2 term already we got here. If you see, already we got the value of a2, that is a naught cc. So the same thing, let me write here, a naught cc into v2 term, this one we can write, so that is nothing but 2gh divided by the whole root over of 1 minus a naught by a1 square, and this is cc square. I hope it is correct. So let's give the square bracket of this. So this is another equation we can give it here. So in the previously, how much equation? Up to 4 equation we went. Now this one we can give equation 5. Okay. So after this, I think you are clear about this. So this may, let me give this a, okay. Now what we need to do here, we can find out the value of CC. Actually CC is, as I told you, that is a coefficient of contraction, like from the orifice meter, from this orifice meter to the second, like section 2. So what is the coefficient of this? So this one, actually, if you remember, we have used a coefficient of discharge term, CD, which used to normally used to use in the venturimeter or orifimeter, and that will have a specific value. And so what I'll do here, I'll convert this term, okay, in the CD. So CD is nothing but coefficient of discharge. Okay, the coefficient of discharge, actually how to find out. Now what is the actual rate of flow, or what is the actual discharge, by what is the theoretical discharge or theoretical rate of flow. So this coefficient of discharge, if you see, always less than 1, always less than 1. Now here you can write the Q actual equal to, so I can write Q actual equal to, I can write CD into Q theoretical, Q theoretical. So here again I can write Q actual equal to CD. This Q theoretical value, we know that we can write A0 A1 root over of 2GH in divided by root over of A1 square minus A0 square. Actually this equation, this is the equation we got from the Bernoulli's equation. Okay, if you have seen the previous videos of venturimeter, there we have derived this equation from the Bernoulli's equation when there is a flow is there. So I can write this Q theoretical equal to this, this formula I can write on behalf of this. So now what I'll do, I'll just take a common of this A1 from this point. Okay, so what will there, let me tell you. So I can get CD into, in the top, if it is there, A1 is there, and I'll take this common of A1 square from here. A1 square, if you take it out, then it will be A1 only, because it is root over is there. So let me write detail. So A0 A1 root over of 2GH, and in the denominator A1 square, let's take it common. So A1 square common is gone out, means A1 square. So it will be, when it is going out, it will be A1 only. And here what will be there? Now 1 minus A0 square is there. Let it keep it A0 square. A1 is not there. A1 taken at common. A1 square I have taken common. So here we'll get A1 square. Okay. And root over 2GS. So now this A1, it will be cancelled here. Okay. Now what we got here? Now Q actual equal to, we can write this CD into A0 root over of 2GH divided by 1 minus A0 by A0 square by A1 square. Okay. Now we got the value of already CD equal to Q actual by Q theoretical. Okay. Now what I'll do, I'll just put this value of this, Q, this one. This is the value is there. This is the one equation. Okay. Yeah. Now what I'll do, I'll just write the value of CD. I'll just write the value of CD. That is nothing but Q actual into, okay, this is root over of 1 minus A0 by A1 square divided by, okay, what I did, just I kept this CD this side, and this total value I'm taking to other side. So what will happen here? Now A0 root over of 2gs. Okay, what I did, just I kept this CD one side and this key actual multiply of this one, so it is going to be reversed here, and just I've done this one. Now what I'll do this, as I told you, I'm going to change this value. Okay, now the q actual value I'm going to put on this. So what is the q actual value? We already got previously, so that is nothing but we can write a naught cc root over of 2gh divided by root over of 1 minus, this is a naught by a1 square into cc square, multiply of this value root over of 1 minus a naught by a1 square divided by whatever the term is here. So we can write this is a naught. Okay, we can write a naught root over of 2gh. So now if you see this value, what we can get, this a naught is going to be cancelled, root over of 2gh is going to be cancelled. Okay, let's cancel this value. Okay, a naught is going to be cancelled. So what will be there? cc by this term into this whole term is there. So what I'll do, this whole term I'll take it to the other in this side, CD side. So what I can get it from, what I can write from this, it's very simple. I can write this term I'm taking to other side. Okay, CD divided by root over of 1 minus a naught by a1 square equal to cc divided by, as the whole term is there, that one, because this already I have cancelled, a naught cancelled. So remaining term what will be there, root over of 1 minus again a naught by a1 whole square into cc square. Okay, now this is the term what I got. Okay, now as I told you, I want to convert this into only one term. I can keep it in the cc term or I can keep it in the cd term. Now because I want to keep this value in the previous equation, I want to put this value in the previous equation, in this equation. So what I'll do, I'll just change the value of cc in terms of cd. So what I'll do, this is because cc is there, I don't want to keep the cc here, so I'll change this value there. Okay, now so I'll write cc equal to, just I'll take it to this side. So that means cd root over of, this derivation is little bit lengthy, but if you remember the steps, it will be easy for us. This square, this I've taken this side. Okay, and in the denominator it will be there as usual, 1 minus a naught by a1 square. Now this is the value of cc. Now what we'll do, this cc value, let's keep it in the, let's put the value, put this value in the equation 5. So if you put the value of in the equation 5, we can write q equal to, this is q equal to a little bit lengthy. Okay, let me write here this value, this equation. Okay, now this equation is nothing but, okay, let me first write this equation, cc a naught cc, and this is root over of 2gh divided by root over of 1 minus a naught by a1 square into cc square. Okay, so let me go to the next page, so it will be easy for us to complete. Yeah, let's start here. Q equal to, we can write what the value was there, a naught root over 2gh. This is 2gh, also you can write in the last. Okay, let me write here, then I'll put the value of cc equal to cd root over this one, the big one is there. Okay, so cd root over of, this is 1 minus, let's write a naught by a1 square, and here it is cc square, and this is divided by Okay, root over of, this is 1 minus, again within bracket it will be there, 1 minus a naught divided by a1 square, and this is the term will be there. Okay, now apart from this, if you see, this is only CC term. As I have written, this is the CC term. Our Q term is again in the denominator, this term is there. So that already root over 2gh I have written. So here also again I'll write the same thing into root over of 1 minus a naught by a1 square into CC square. Now if you see, this common term is there. There is a common term is here. So we can cancel that. So what I'll get here, Q equal to, let's take this CD term in the first, CD, and this is a naught root over of 2gh, root over of 2gh divided by root over of 1 minus a naught by a1 square. And finally, if you want to write, I'll take this common of a1 here. Again, I've just, this not common, I'll just solve this one. So finally what I'll get here, Q equal to CD a naught a1 root over of 2gh divided by root over of a1 square minus a naught square. Now if you remember, this was the previous equation what we got in the venturimeter type. Okay, the same equation we got it here also. And always keep in mind that the coefficient of discharge value of orifice meter always less than the venturimeter, and the CD value of this orifice meter always varies from 0.4 to 0.6 or 7, something like that. It will be vary, and it is always less than the venturimeter value, because venturimeter value we have seen CD value was 0.9598 near about 1. So I hope you understand the derivation of this orifice meter, and this is all the total details of this orifice meter. Like we have started from this Bernoulli's equation, then we have applied this continuity equation, and here I have taken this V2 value, then I put the P2 value here. Then after that, just to we have solved this equation, and just CC term came, coefficient of contraction, just we have converted into CD, and finally we got this equation. So I hope you understood this equation. If you are having any kind of query and doubt regarding this, you can give a comment on the comment box. Thank you all.